Okay. Hi, everybody. And we start this lecture from the Kepler's third law. Last time we discussed Kepler's laws, and today we have to finish this discussion. Well, you know the Kepler's third law. We have already considered it briefly. If you have a planet of mass m orbiting a sun of mass capital M, and the radius or the distance of this planet from the sun is r, and the planet goes with velocity v, we assume for simplicity that the orbit is circular at first. If the orbit is circular, then the force of gravity, gravitational interaction, causes the centripetal acceleration of this mass, so that the second Newton's law holds in this case. And the force is equal to the force of gravity, which is the Newton's law of universal gravitation. And the acceleration can be expressed using the orbital velocity of the planet over the radius. And substituting this expression into this Newton's second law, we note that the mass of the planet will cancel, and one radius of the orbit will also cancel. And what we obtain will be gamma capital M over r. Gamma capital M over r will equal velocity squared. If we recall that velocity is the length of the orbit, that is 2 pi r, divided by the period of revolution, then we obtain from here that gamma capital M over r will be equal to 2 pi squared. It's 4 pi squared radius squared over t squared. And from here, we immediately obtain that radius cube divided by period of revolution squared equals gamma capital M divided by 4 pi squared. Gamma is universal gravitational constant, and M is the mass of the sun, which is the same for any planet, and 4 pi squared is another constant. So what we have on the right-hand side of this equation is constant for all the planets. It's the same number for all the planets. It doesn't depend on the planet mass. It doesn't depend on the planet radius. It's the same number for any planet. So we obtain the third law of Kepler, which says that the cube of orbit radius divided by the period of revolution squared is constant for all the planets in the solar system. Also, it should be constant for all the artificial satellites of the Earth, or all the artificial satellites of the Mars, for example. So whenever you have a gravitational interaction and the central body which attracts the orbiting stations, then you will have this relationship, which is Kepler's third law. Law number 3 by Johann Kepler. Actually, the planets do not move along circular trajectories. You know that the orbit of each planet, according to the first law of Kepler, is an ellipse. So if I draw an elliptical orbit, then the sun will be in one of its focal points. So for example, here is the sun of mass capital M. And the planet orbits the sun moving along the elliptical orbit. In this case, what will change in this law? Nothing. Nothing will change. But r should be, in this particular case, another quantity. It will not be the radius of the circle, because here the orbit is not circular. R will be a semi-major axis. So if we draw a diameter or a section of a direct line which goes through both focal points of the elliptical orbit, then the length of this section AB will be called a major axis of the ellipse. There is another axis which is a minor axis, but we don't need it now. We need the major axis, and we need half of this major axis, which is called semi-major axis. The semi-major axis will be the quantity r, which enters into this formula. So if the orbit is elliptical rather than circular, then the formula remains the same, but the meaning of this quantity r will change. Now it will be the semi-major axis of the elliptical orbit of the planet. So that's what is there to say about the Kepler's law. And now we will have a demonstration, a computer demonstration of laws of Kepler. So that's a computer screen, and the calculation of motion, of planet's motion, will be visible here, the result of calculation according to Kepler's laws. So if we start, you see the planet moving about the sun along the elliptical orbit, and the velocity of the planet is not the same. You showed us. Okay. And note that initial velocity is large, and then here the velocity is smaller, so that the area swept by the radius vector is the same if we measure this area during equal time intervals. So what this law of Kepler says, certainly the elliptical orbit is the first Kepler's law, and the fact that during equal time intervals, the radius vector showing to the planet sweeps equal areas. That's what you have seen on this demonstration. Now we start the motion of some body like a comet. Okay, it goes along a parabolic trajectory, but the same law of equal areas swept during equal time intervals will be applicable here. The same Kepler's law, equal areas swept during equal time intervals. That's it. That's what really happens when the comet goes along a parabolic trajectory. Now we see the same thing when the trajectory is hyperbolic. And you recall that the trajectory is parabolic when the total energy is 0, the total energy of the moving body is 0. And when the total energy is larger than 0, then the trajectory will be hyperbolic. But the same Kepler's law will hold, that is, equal areas will be swept by the radius vector during equal time intervals. The same here. Okay, and the last Kepler's law. Now we imagine, suppose that several planets, several bodies are launched at the initial moment of time. Okay, let's start it. So, here we can see the areas shown in different colors, the areas swept by radius vector, covered by radius vector. are shown in different colors. That's the way the planet moves. That's it. Okay. И теперь третий закон Кеплера. That's the second Kepler's law. And now several bodies, several celestial bodies will move along different trajectories. The first trajectory is the circle. You see the red planet, the red body, red color body moves along the circular trajectory, and the second moves along the elliptical, which has twice as large, or which has slightly larger semi-major axis, and the period of rotation is smaller for a larger orbit. And if you look to larger and larger orbits, you see that the period of rotation, period of orbital motion is smaller when the semi-major axis is larger. So this is the demonstration of Kepler's law number 3. Okay, thank you. Спасибо. Last lecture we discussed the energy relationship for a celestial body, and the energy relationship was this. The velocity, it's not the total velocity of the body, but just the radial component of the velocity, which is indicated by index r squared over 2, plus the angular momentum per unit mass over 2 r squared. That is the distance from the celestial body to the sun, minus gamma capital M over r equals minus total energy. This way of putting the total energy underlines that the total energy is if it's positive, then this expression should be negative. If this quantity is positive, then the total energy is negative. When that happens, when we have a finite motion of a planet. You remember that these last two terms were denoted as an effective potential in gravitational field. All this was discussed during the last lecture. And we have drawn the picture, the graph of the effective potential as a function of distance to the sun, between the planet and the sun. And the curve was something like that. And we discussed that if the planet moves along an elliptic orbit, then the distance from the planet to the sun varies with time, and there is the smallest distance, r1, and the largest distance, r2. And generally, any distance is between, in other moments of time, any distance is between these largest and smallest values. So if we choose here some energy minus epsilon, then we obtain the smallest distance and the largest distance. And that corresponds to the motion along the elliptical orbit. What if the orbit is circular? If the orbit is circular, then the radius, or the distance from the planet to the sun, remains constant. How can it be? It means that the constant radius can only be realized when the total energy is this one, when the effective energy is here and the planet moves according to this. On this function, the planet is here at the minimum of effective energy, effective potential. So if the planet is moving between this point and this point here, then it goes from between the larger and smaller radii. But if the radius is constant, the orbital radius is constant, then the planet is necessarily here at the minimum point of effective potential. So in order to find this quantity, we can take this function, effective potential, as a function of radius, and we can find the minimum of this function by taking a derivative in the usual way. We take the derivative with respect to r, and if the derivative is 0, then we are at this minimum point. How this function depends on the radius? Here is the dependence. A constant divided by radius squared minus another constant divided by radius. So this function is somewhat more complicated than usual. The radius is in denominator. So I will introduce another function, another variable, which will be x equal 1 over r. In this particular case, the effective potential can be written as L squared x squared divided by 2 minus gamma mx. And we have to take a derivative of this function with respect to x, and it will be L squared x minus gamma capital M. And the derivative should be 0 if we want to find the conditions for this lowest point. For this minimum point here, the derivative is 0 of this function. So we have taken the derivative of this function with respect to x, and from here we can immediately find x equal to gamma capital M divided by L squared. But x is 1 over r, and so we can immediately find r, which is equal to L squared divided by gamma m. What is L? It's angular momentum per unit mass. So this is the angular momentum of the planet divided by mass. Angular momentum is radius times mv. But in this particular case, when we find the angular momentum, we don't have to take into account the radial component of the velocity. The radial component, the component directed along the radius, is taken into account here by the first term. And the second term takes into account, as you remember from the last lecture, only the tangential component of the velocity. So this quantity will be radius squared and velocity tangential component squared, and divided by gamma m. From here we see that one radius will cancel, and velocity squared, tangential velocity squared, will be equal to gamma m divided by r squared. I have lost somewhere one radius. Where is it? I don't see. Where is the mistake? Who can find it? The bottom line, this one?
Because you have r, that would equal r squared, tangential velocity squared, next r.
Where should be another r? I don't see. Do you see the mistake? I don't see the mistake. It should be somewhere, it should be somewhat different. Oh, yeah. That's it. Yes, certainly. We should take this expression, and we should take rather this instead of this one. So, yes, if we take these two parts of the equality, then one radius will cancel, certainly. One radius will cancel. And what we will have will be tangential component of velocity squared will be equal to gamma m divided by r. Gamma m, because one r will cancel. And so here we will have just gamma m and r in the first degree. So yes. Gamma m divided by r. That's the correct, absolutely, yes. That's the correct way of reasoning. So if you look at this formula for the tangential velocity, and I started from considering the circular motion. The circular motion corresponds to the minimum of this function of effective potential. Then the radius of circular motion will be in this way will be related to the velocity of the circular motion. If you look at this function, and if you look at this function, which we have already obtained from different way of reasoning, then you can see that these two equations are absolutely identical. So this one was obtained from the second Newton's law, and this one was obtained from the effective gravitational potential, which we have differentiated and found the minimum of this function, and from the condition for minimum, we have found the relationship between the velocity and radius. Absolutely the same result obtained using different method. So what is the tangential velocity? That's just the velocity of circular motion. That is the velocity of circular motion. That is the velocity, tangential velocity. And so from this formula, we what is the tangential velocity if the satellite orbits the Earth at a low orbit? That is, the radius of the orbit actually coincides with the radius of the Earth. In this particular case, that will be the velocity, the first cosmic velocity, or the orbital velocity. That will be from this formula a square root of gamma m divided by radius of the Earth, if you take it. So from here, we immediately obtain the formula for the first space velocity, or first cosmic velocity, or orbital velocity. Well, you know this formula. We have already discussed it last semester. Today, I only wanted to demonstrate that it can be derived from absolutely different approach, using absolutely different approach based on the effective gravitational potential. If we look at this important relationship and think about the escape velocity, what should happen if somebody escapes the planet and goes to infinity? If some spaceship wants to escape the planet and go to infinity away from the planet, or if some spaceship wants to escape the sun and solar system and go at infinity from the sun, what should happen in this case? First of all, the total energy should be zero. We discussed it, that when the moving comet or spaceship goes at infinite distance, its energy must be either zero or larger than zero. If the energy is zero, then the trajectory will be parabolic. If the energy is larger than zero, then the trajectory will be hyperbolic, hyperbola. But we want to calculate the minimum possible velocity of such object, which is called an escape velocity. So we need to take into account the minimum possible energy. We don't need large energies. It's obvious if you are able to impart large velocity to an object, it will have large energy and it will escape the sun and escape the Earth and anything. It will move easily to infinity. But we want to calculate the minimum possible energy and correspondingly minimum possible velocity of such an object which is capable of going to infinity. So the first thing we have to take into account here will be 0 epsilon. Another thing, we don't need for such an object to have a tangential velocity. We don't need any tangential velocity. Tangential velocity should be 0. And therefore, for such an object, along with tangential velocity, angular momentum L will be 0. Angular momentum, because we don't want such an object to orbit the sun. We don't want it to orbit the planet. We want it to go directly away, so that angular momentum will be 0, because angular momentum is related to tangential velocity, and radial velocity is taken into account by the first term here, and tangential velocity is taken into account by the second term here in this formula. So if we take these two conditions into account and apply these two conditions here for this equation, we will obtain from this equation, we will obtain from here that the first term will be here, radial velocity squared over 2. The second term is 0. Then we will have minus gamma capital M divided by R. And the last epsilon is 0. So that will be a condition for such a motion with 0 energy, that is to move at the infinite distance, and with 0 angular momentum, which means that we choose to move away along the straight line. So from here we can immediately obtain the velocity which is needed for such a trip. That will be a square root of 2 gamma m divided by r. That is the dependence of the velocity versus distance r to the planet. So if such a spaceship is launched from the Earth and moves at infinity, then the velocity of such spaceship will depend on the distance from the Earth according to this formula. And if we take for the distance between the spaceship and the Earth, the radius of the Earth, then we will obtain the maximum velocity. The smaller the radius, the larger the velocity. So if the spaceship is on the surface of the planet, then this small r will become the radius of the planet Earth. And that radial velocity will become a second space velocity or escape velocity, and that will be given by 2 gamma capital M divided by radius of Earth. So if you compare the second space velocity and the first space velocity, then you can easily see that the second space velocity is equal to the first space velocity square root of 2. The escape velocity is by square root of 2 larger than the first space velocity, which is the orbital velocity. The velocity needed to orbit the planet of radius r and mass capital M. All this is very simple, and it was known in the 19th century. It was well known. All these velocities were known. And there was such a scientist whose name was Laplace. Have you heard about him? He imagined that there is such a body, such a heavy mass m, with such a small radius, that the velocity is so large that it becomes equal to the velocity of light. You see, the velocity, the escape velocity, is proportional to the mass of the central gravitational body and is inversely proportional to the radius of this body. So if we have a very heavy, very large body and small mass, small radius, a very, very large mass contained in small volume, in a small radius, then the velocity can be made very large. And suppose this velocity is equal to the velocity of light. Nothing can reach the velocity of light. So it means that nothing could leave such a gravitational body. Nothing could ever escape. And if the escape velocity is equal to the velocity of light, it means that this formula will give you the radius of such an object which cannot be, which no object can leave such a gravitational mass and can fly far away from it. And so Laplace guessed that if there is such an object in the universe, then only the light can escape it. And if you go a little bit closer to this object, if the radius becomes a little bit smaller, then you will need larger velocity than the velocity of light. It means that from inside such a radius, nothing at all can escape such a strong gravitational field. Even the light cannot escape it. So that will be what is known today as the black hole. And the radius of the black hole, from here will be found as 2 gamma capital M divided by c squared. That is the radius of the sphere, such that from inside the sphere nothing can leave the gravitational field, the strong gravitational field of this capital M. Nothing can leave, because in order to leave this gravitational field, you need to move with the velocity of light or even higher than the velocity of light if you go just a little bit beneath this radius. And this radius is called event horizon. This radius is called an event horizon for a black hole. And event horizon is such a surface of spherical surface of radius r, such that nothing can escape from inside it. Nothing, even the light cannot escape this gravitational field of such a heavy mass. So if even the light cannot go out, then this is This is called a black hole, and such is the radius of the event horizon, which surrounds the black hole. Nothing can escape from inside the event horizon. Well, there was a bell indicating a small interval, but we started late today, so let's continue working without an interval. So if you have a black hole, nothing can leave it from distances smaller than r. And Laplace calculated and obtained this formula from such a simple formulas which I have shown you before. Today, black holes and strong gravitational fields are described by a general theory of relativity, which is a complicated theory which takes into account the distorted time and space, or warped time and warped space. And it's a mathematically complicated theory, but if you solve all the equations, which are quite complicated, I repeat it again, then you will obtain for the radius of event horizon the same formula. It's very interesting that classical theory, classical approach, produces the correct result, the same result which is produced by the general theory of relativity, which was created by Albert Einstein. So that is the correct formula, which is in compliance with modern theory, regardless of the fact that this formula was obtained using the classical, simple classical approach. To finish with gravitation, we need to consider one more thing. The last thing we will consider will be a Gauss theorem for gravitational field. A Gauss theorem there is a Gauss theorem for electromagnetic field and a Gauss theorem for gravitational field, and the two theorems are practically identical as far as mathematics are concerned. I will write you, first of all, I will write you the final result of the Gauss theorem, Gauss's theorem. The final result is that if you have a gravitational mass and you surround this mass by an arbitrary closed surface, so this is not a trajectory, this is not a line, this is a surface. A surface. Well, the simplest surface is a sphere, and imagine a sphere which has been deformed in some way. So this is an arbitrary surface. Then, if you calculate such quantity, which is called the flux of gravity field, through this surface S, a flux through this surface, arbitrary surface, then you will obtain minus 4 pi gamma capital M. Now we will discuss. That is the final result. That is the formulation of the Gauss's theorem. Now we will discuss it. First of all, what is striking about it? It does not refer to a particular surface. The form of the surface and the shape of the surface and the dimensions of the surface have nothing to do, have no influence on the final result. The final result does not depend on what surface you take. That is the first important thing about the Gauss's theorem. Then we will discuss what is the flux. The quantity of flux was introduced to physics when people considered the flow of liquid through the pipe. So this is the pipe, and the liquid flows here, and the liquid has some density and it has some velocity. And if we have a cross-section area of this pipe, then it's easy to calculate the flux of the liquid through this cross-section area. The flux of liquid will be the density of liquid times the velocity times the area. And it gives you the density is kilograms per meter cube, and here you will have meter cube per second. So meters cube will cancel, and you will have how many kilograms per second flow through this tube. That's the physical meaning of such a quantity as flux. It's simple when you consider the flow of liquid. The flux is how many kilograms per unit time flow through the cross-section of this pipe. When people thought about this quantity, they immediately noticed that if you take a different area here, then the flux will not change, because the number of kilograms passing through this tube will remain the same. How to calculate it, how to make formulas conform with this conclusion that the flux shouldn't change on the shape of this area which you take here across the tube. It's easy to see that if we introduce a perpendicular vector, a unit vector n, which is perpendicular to this surface area, and if we introduce such a quantity as scalar product of vector velocity by the area and unit vector perpendicular to the area of some cross section, then because the scalar product will include a cosine of vector between the velocity and unit vector which is perpendicular, it will include the cosine alpha. Then it means that if you choose larger or smaller alpha, that is, if you choose some different area, some different cross section of the tube, then the result will not depend on alpha. The result will not depend on alpha, because if you take n cosine alpha, you will have to take this vector which will correspond to the original surface. So such a result will not depend on the angle of inclination of this area. So if we compose such a quantity as flux equal to density and scalar product of velocity and area, then this flux will not depend on which area we take, how the cross section is inclined inside the tube. For any angle alpha, the result will be the same, which corresponds to the meaning of this quantity, which is just a number of kilograms flowing here, kilograms of liquid flowing per unit time. That quantity should not depend on how you calculate the cross section, how you take the cross section of this tube under what angle. So people understood that flux should be calculated using the scalar product. And then when electromagnetism was developed, such a quantity as flux applied to electromagnetic field was introduced, and the flux through a small area delta S was determined as scalar product of the vector of field strength, electric field strength, and the vector of delta S. Vector of delta S in magnitude is equal to some area, to some small area, delta S of the surface. And the direction of this vector is perpendicular to this surface, exactly like what was shown in this picture. This vector is perpendicular to elementary small surface, and the dimension, the length of this vector is equal to the surface. So if we introduce such a vector of surface, a vector of area, then scalar product of electric field strength and such an area, such a small area, is by definition is determined as the flux of electric field through this surface. What is the strength of electric field? In electricity, this is a force acting on a unit charge or on a charge divided by the electric charge in electricity. In gravitational field, the strength of the electric field is defined in the same way as the force acting on some mass in gravitational field divided by the mass. So in electricity, we divide the force by the charge of a charged particle. And here, the role of the charge is played by the mass of the particle. So the force in gravitational field divided by mass. And the force is equal mg. If we divide it by mass, we obtain that the strength of the field in gravity is equal to acceleration of free fall. Nothing else but the acceleration of free fall. And that's the reason why I have chosen to denote this quantity by g from the very beginning. The strength of gravitational field is the acceleration of free fall. And now we will define the flux in electrical field and the same quantity flux in gravitational field. That will be the, instead of the strength of electrical field, we use the strength of gravitational field, vector g, the acceleration of free fall, and multiplied by an element of area, delta S, a scalar product. So we have defined what the flux is in gravitational field. The flux of gravity field strength, which is acceleration of free fall. Now we are ready to calculate the flux if the gravity mass m is surrounded by a spherical surface. Suppose that the surface is spherical and has a radius r. Then the total flux of gravitational field strength through this spherical surface, total flux in gravitational field, will be equal, according to this definition, acceleration of free fall at the distance r from the central mass times the area of the spherical surface, which is 4 pi r squared. And we have to take scalar product between these two vectors, scalar product, and mind that the acceleration of free fall is directed to the center, towards the mass. And the vector delta S is directed, has the outward direction. That is the unit vector directed outward from the spherical surface. So that the scalar product of these two vectors will be negative. So we will have negative. I immediately take into account the angle between these two vectors, which is 180 degrees. So I don't write vectors here. I use the scalar notation, but I immediately take into account the direction of these two vectors. As they are oppositely directed, the scalar product between these two vectors will be negative. And what about the magnitude of this vector? That will be 4 pi r squared, and the acceleration of free fall will be gamma m according to Newton's law of universal gravity r squared, the same r squared. So radius will cancel, and what we obtain minus 4 pi gamma capital M. The result for the flux in gravity field is what I have shown you from the very beginning, with the only difference that I have taken here a spherical surface, while we need to take an arbitrary surface. I have taken a spherical surface, and we need to generalize this result for an arbitrary surface. And we have to prove that if we somehow deform this sphere, deform it to obtain any other form, any form, then the result of the flux through this deformed surface will be absolutely the same. It will not depend on the shape of the surface. This can be proven in very simple way, very easy way. We have to consider a small angle, a small central angle, for example, somewhere. Let me draw another figure. So this is the central mass, and I consider some central angle, and this is the surface of the sphere of radius r. And if I deform the sphere in any arbitrary way, then this small surface area delta S will take some other form, like it will be somewhat inclined, because the surface is deformed in arbitrary way, so that the normal to this surface, a unit vector perpendicular to the surface, will look sideways. And we have already seen that when we incline this surface, incline the section area at some angle, the result in calculating the flux will not depend on angle alpha. For any angles, the result will be the same. Certainly the same logic works here. If we somehow deform the surface, and the surface area delta S will become delta S prime after we have deformed it by some angle, then the result of calculating the flux will be the same as we have already shown it, because there is a scalar product, and so that scalar product includes cosine of angle between these two vectors, this vector and vector g. And the cosine of these two vectors will work in such a way that whatever angle you choose, the final result for the flux through this small surface area delta S will be the same. It will not depend on the angle. If it happens for every small area of the surface, then the same will be true for the whole surface. And whatever deformation of the surface you imagine, whatever deformed surface you take, the flux through this deformed surface will be the same. It does not depend on the shape of the surface. That's it. We have proven the Gauss's theorem for gravitational field. And that concludes our consideration of gravity and central fields. That's all we had to discuss about gravitational interaction and central fields and the laws which apply to the motion of celestial bodies or artificial satellites in gravitational field. That's all. No more information on gravity. So now we proceed to consider some other issues, and the next issue will be the energy of rotational motion of solid body. The next topic we consider will be the energy of rotational motion of a solid. Speaking about rotational motion of a solid, you should remember the Koenigs Theorem. Koenigs Theorem says that the energy of solid measured in any reference frame, arbitrary reference frame. I will denote arbitrary reference frame by using letter A. So the energy EA, that is a kinetic energy in arbitrary reference frame, will equal the energy of the same body in the reference frame associated with the center of mass plus the total mass of the body, the velocity of the center of mass squared over 2, where the velocity of the center of mass is measured with respect to this arbitrary reference frame A. Do we remember the Koenigs Theorem? We have proven it. We considered it some weeks ago. And we proved that the kinetic energy of an arbitrary solid body, if calculated in the center of mass system, then its minimum possible kinetic energy, because the velocity of the center of mass in the center of mass system is 0. This term will be 0 if we measure the kinetic energy in the center of mass system. But if we measure the kinetic energy of the solid in some other arbitrary system, which moves translationally with respect to the center of mass system, and the center of mass has the velocity Vc with respect to this new reference system, then in this new reference system the energy, the kinetic energy, will be calculated according to this formula. That will be the energy in the center of mass system plus the energy, kinetic energy, such that if the whole mass of the body if the whole mass was concentrated in the center of mass point, if the whole mass of the body was concentrated in its center of mass, then this is the kinetic energy of motion of mass having the velocity Vc. Note that different points of this solid may move with different velocities, but we take the total mass of the solid body and the velocity of the center of mass squared, and this velocity is calculated with respect to the arbitrary reference frame, new reference frame. Such was the Koenigs theorem. We already proved this formula, we derived it, and we discussed it. Now, if we consider the motion, the rotational motion of solid body, I will take a disk for a solid body. That's a disk of mass m, which rotates about axis z. So it rotates in this fashion. That is the center of mass of the solid body. It has many points. The solid body consists of many material points, and the mass of each point may be denoted as m number k. We can number the points, that is the first point, the second point, a third point, etc., point number k. So that's the general way to take into account an arbitrary point inside the solid body. Then, in this case, the energy, the kinetic energy in the center of mass system will be the sum of kinetic energies of all the points of this body, and each point will have kinetic energy mk, its own velocity squared over 2, and the velocity of this point may be calculated like, may be shown here like some vector. This point also goes along its circular trajectory. And different points have different velocities and different masses. And the velocities are different because different points have different distance r, k, from this z-axis of rotation. So that each velocity vk is equal to the distance of this point from the z-axis times omega, the angular velocity of rotation of this body. So that the formula for kinetic energy will take the form mk times rk squared omega squared over 2. Certainly, omega is the same for all the points of solid body. Omega is the same parameter, same quantity. The solid body rotates at some angular velocity, and that will be the angular velocity for any point, for characterizing all the points inside this solid body. So omega is constant. It can be taken out of this sum, and also 2 is constant, so we can take it as, we can write it as omega squared over 2, and here we will have the sum over all the points of the solid body, mk times radius k squared. This quantity you know already is called a moment of inertia of solid body. So we obtained the formula that the kinetic energy of rotating solid body can be written as its moment of inertia with respect to the axis of rotation which goes through this center of the mass, center of mass, omega squared over 2. Where the moment of inertia is defined, that is, this formula is the definition of the quantity, is defined as mk rk squared, and such a sum is taken over all the points mk of the solid body. So in this sum there are such terms as m1 r1 squared plus m2 for the second point plus m3 for the third point, etc., etc. There may be thousands of points, and that is the general expression for any arbitrary point number k. That's the definition of the moment of inertia. And we will talk a little bit about this quantity and how can it be calculated. First of all, let's discuss the important thing. What if the points k are not distinctly defined separate points, but the mass is distributed over the volume of solid body? How can we change this formula to take into account distribution of mass, arbitrary distribution? Then, in this case, the sum will turn into an integral taken over the volume of the body, and under the integral there will be r squared, that is the radius squared, times the mass of the small part of the body. The small part of the body will have a very small mass, so that will be a dm, a differential of mass, an infinitely small mass of infinitely small volume of this body. I already explained to you what we mean by saying infinitely small. In physical sense, it doesn't mean that the infinitely small volume may become smaller than the volume of a molecule or smaller than the volume of an atom. In no way. Physically, in physical sense, infinitely small is a small volume which comprises many, many atoms, maybe 1,000, 10,000, maybe a million, but many atoms. Anyway, that's a small amount of matter, small volume comprising many atoms, but the mass is small, and we can mathematically denote it as dm. That's what we mean when we say infinitely small. When physicist is using infinitely small, these words infinitely small, he means something different from what mathematician means when he uses the same words. In mathematics, infinitely small is infinitely small. In physics, infinitely small is actually not infinitely small, but very small. But anyway, finite. Some small but finite volume. That's what we mean in physics. In order not to contradict the finite volume of atoms, in order not to go inside the atom, which will absolutely make an absurd calculations. So, but mathematically the result will be the same. Yes, the same. So in order to calculate the moment of inertia of an arbitrary body, we must be able to find such an integral. And now we will consider some examples. First example, we will consider a rod of mass m and length l, and the rod may rotate about the axis O, and we need to calculate the moment of inertia of such a rod, and the moment of inertia will be this integral r squared dm. What is r? If r is the distance of some small mass dm, we take a small mass dm here, and r is the distance of this mass, of this element dm from the axis of rotation. In order to calculate such an integral over the whole volume, how to calculate over the whole volume? It means that we must imagine, we must assume this total body divided into very small parts, and we have to add all such expressions r squared dm for every small part. That is, we have to integrate from 0 to L, and also we have to find what is dm. In order to find what is dm, we must calculate the density of this rod, which in one-dimensional case, one-dimensional density will be mass of the unit length. The mass of the unit length will be total mass divided by length. In this case, the mass dm of some small element dr will be the mass of the unit length times dr, and that will be m divided by L, which is the linear density, dr. And that quantity should be substituted here in the integral, and what we obtain will be m divided by L dr. M divided by L is a constant. It can be factored here before the integral, and the integral is from 0 to L r squared dr. That will be m divided by L, which remains on its place unchanged. And what's the integral of r squared? That will be r cubed divided by 3. And we have to take it within the limits from 0 to L. And that will be m divided by L. When r equal to L, we will obtain L cube, r cube, in r equal to L, then r cube will be equal to L cube divided by 3. Minus 0, we substitute 0 instead of r and obtain 0. So that will be m L cube divided by 3L. Certainly one L will cancel, and we obtain mL squared divided by 3. So that the moment of inertia of all this body of all this rod with respect to the axis which goes perpendicularly to the rod through one of its ends, the moment of inertia will be ml squared over 3. Now it's proper time to consider the Steiner's theorem, Huygens-Steiner theorem. Huygens-Steiner theorem, which allows one to calculate the moment of inertia with respect to an arbitrary axis if we know the moment of inertia about the axis which passes through the center of mass of the body. So there is an arbitrary solid body, and it has the center of mass, and there is an axis of rotation which passes through the center of through the center of mass of this body, and we need to calculate the moment of inertia of this body through about an arbitrary axis A, which does not go through the center of mass. So if we take any point of origin here, with respect to which we will calculate all the radius vectors, and we have some point M, K, in this rigid body with its radius vector RK, and we have another arbitrary point A prime, and the radius vector R K prime, and the second point A prime shall have a radius vector R with respect to the original point A. Then from this triangle we may write that RK, this vector, equals capital R plus small rk prime. When we calculate the moment of inertia, we will have to calculate such quantities as mk rk squared. So we have to know what is rk squared. We have to calculate such a sum in order to calculate the moment of inertia. So if the moment of inertia by definition is such a sum, then we just substitute rk here in this formula and obtain mk, and rk is equal to this expression capital R plus small rk prime and squared. So that will give us mk, and inside the round brackets we will have capital R squared. I remind you this is a scalar product of vector r by itself. R times r, r squared, plus small rk prime squared, and plus two scalar products of vectors capital R and small r with index k prime. That's we just open the square of the sum of two terms. If we continue this formula, we will notice that in the first term, mk capital R squared, capital R is constant, and it can be taken here. and we will have the sum of all masses, which will be just the mass, total mass of the body, total mass of the solid body, plus the second term will give us the sum over all points mk radius rk prime squared. This term is obviously, by definition, a moment of inertia prime with respect to point A prime, with respect to some axis going through point A. And plus the last term, which will be 2r capital, and I will put it this way, mk rk squared I rk vector rk prime over all the points. What is the sum of mk rk? The sum of small masses multiplied by the distance of these masses from some points. What is this? This is by definition of the center of mass. This will be equal to, by definition of the center of mass, total mass of the body, the radius of the center of mass with respect to point A prime.